And we're off with the last lecture in this series uh, of the summer machine learning course. It's been a long 8 weeks, and so thanks for sticking with us. For those of you who did, logistics first. Couple of things. So we will have a final project presentation next Sunday, which is at the recitation time. So it's not out of the ordinary for any of you. On Saturday, we reserved a slot, a slightly later slot, to allow you to practice your presentations, get some feedback on the slides, on anything else that you need to cover. And so the reason being, there will be a panel of judges on Sunday from Google, MIT, CMU, some people in industry, some researchers, some students. So it gives you a whole spectrum of people that you would want to get feedback from in order to take these ideas further. And the reason we're doing this is because the teams that have presented have really good ideas. And so it would be beneficial for you to actually get feedback from real people who are not us. um, um, who have not seen any of these ideas before, to comment on like what is the kind of potential for the idea that you're pursuing. And we do see at least some of I see most of the projects turning into very decent publications, workshop or conference publications. And it's not a stretch to say that you can write a paper about the work you're doing. So um, given that most of your students and would benefit from like explicitly having done research and published a paper prior to whatever you do next in your life and career, I think that would be a great idea. And I'll also mention how we plan to continue mentoring you if you want on these research projects. But more on that next week. So far, all you need to know is there will be a project presentation on Sunday. There will be a dry run on Saturday for those of you who want it. And so prepare your slides accordingly. Please submit the details in the form that we will release right after the lecture today. So we can plan the logistics for these two sessions. Again, for those of you not who joined just a little bit late, we will have judges who hail from industry, academia, good companies, big universities, and can give you good feedback. The bottom line being they can give you good feedback on how to present these kinds of projects and take them to the next level. Cool. So with that, and we will have a recitation tomorrow. So please be sure to sign in. With that, we can get started with the lecture series. The last lecture in this series, which is on advanced recurrent neural networks, attention, and going from RNNs to transformers, the whole paradigm shift. Transformers being the current, I wouldn't say current, but like transformer based architectures are the current state of the art in a lot of NLP applications. So that's part of the reason I want to get to transformers, but also we started at very vanilla RNNs. So we have to build up some concepts before we get to a stage where we can discuss transformers. So let's get started. So if you remember, this was the diagram we left the last lecture off at, where we said, okay, there is a recurrent neural network where each state is affected by some previous hidden state that captures information that comes before this input in a condensed form. So we use this information in order to generate the output at that stage along with the input at that. When I say stage, I mean point in time typically. So we have hidden state update. Uh, at each point in time, your hidden state also gets updated with the current information. So you have a weight matrix times the current input, you have a weight matrix times the previous hidden state, and you have a certain bias added to it. And this phi can be any nonlinearity of your choice. Then you have the observation that is produced from this hidden state and this bias. So the general idea being there is a hidden state that captures all of the information that comes before it. We saw some problems that have to do with the fact that this hidden state, it does not actually in theory does not actually do in practice what it is supposed to do in theory, right? And we said, okay, like sometimes you need to add more ways, you need to add more correspondence to how we deal with information and knowledge in our minds, because if neural networks are supposed to represent our our mental processes, then they should reflect what nuances of memory we have. And with memory, you get to this idea of, okay, you remember certain things, you forget certain things, all past knowledge. It's not like you remember your grades from back in first or second grade. You know that you got some grades, but it's not necessary that you remember those. So there is this notion of forgetting some information that is not as important. Whereas your parents' birthday is probably something you don't necessarily forget. Well, some of us at least. um, I'm, I remember my parents' birthday. Never mind. So the point being, long short-term memory came about when people ran into problems with recurrent neural networks, and they said, well, we want to remember some information, we want to forget some information, so let's add some nuances into recurrent neural networks to add this little bell and whistle on top that says, well, we play around and we forget some of the information and we remember some of the other information, and we want to learn the correct dependencies so that you can make better predictions. So what this is saying is, let's now incorporate this idea of a reset gate where it forgets some things based on certain rules that are learned. That's about it. This is not complicated at all. So input and hidden state go to output. Now you have an element that says forget some of the past. So maybe for some elements, you don't consider the hidden state. So your forget gate shrinks your values towards zero. Um, Again, fairly straightforward. The idea of forgetting is to not have as much of a contribution of a certain uh, hidden state to a certain prediction. Um, and the output gate relies on this decision of whether the hidden state is used for the output generated by the LSTM. Now, the real novelties that come about with the LSTM is this idea of a memory cell. So in addition to your hidden state, and again, what I want you to focus on here, I should probably highlight, is the slides are a bit tedious in the sense they have a lot of content, which is great, especially if you're not being taught this by the actual lecturer, but it gets a bit intimidating to look at this all at once. Anyway, so I'm saying typically your hidden state and your input contribute to your output, but now we add this element of a candidate memory. And let's talk about what this candidate memory is, right? So we want to have a forget mechanism inside this process of inside the sequence of recurrent cells in order to forget some items. And so we start with the same idea for all of these. Non-linearity over the inputs, the hidden states, and the biases. Next, what we go on to is this idea of candidate memory. And initially for the I don't call it the memory because this is the initial state of the memory, so it's just called candidate memory. There is nothing complicated about that. What I want to say is, this is the key innovation. Damn it, I will have to clear. Yeah. So this is the real innovation that came about with LSTMs. That says, okay, now I want to have this memory element, and the way I calculate this memory element is by taking tan H, again, non-linearity, over the inputs, over the hidden states, and adding a certain bias to it. And I also want to use now this candidate memory. This is up till here. Sorry. This is candidate memory up till here, right? After I calculate this memory element, I want to actually determine whether I should forget what comes before it. So this previous cell is multiplied by a forget gate. So we have this memory going on. We have this memory element that we are calculating. And to this memory element, we either add or we do not add the previous memories. And that is how we include a forget element in this vanilla recurrent neural network. It's as simple as this. It is just like adding candidate memory, maybe adding the previous memories, maybe not. The rest of it is the same as you would do otherwise, right? And you obviously want you're using the memory for calculating your output, so you want it to include the inputs. So you take the Hadamard product of your candidate memory with your input, and that is how you calculate your output. So this memory element now goes through another nonlinearity and gets element wise we take an element wise product with the output. So yeah, two aspects to this. First, calculate the candidate memory. Oops, let's clear all of this. Maybe a red pen is best. I want it to be a little thicker. So first, consider your candidate memory, consider your forget gate times your previous memory element, take your inputs, element wise product with the candidate memory, and then take all of this, pass it through a nonlinearity, and take an element wise product with the output gates. I don't think I want to say anything more about that. If there are questions, pause me, make me go over all of these details in like line by line, but generally you can see that all of these elements are more or less the same for your input gate, for your forget gate, for your output gate. What really comes in is this part, memory, and then the hidden state update. Yeah, I don't think I have anything more to say. So turns out, so the in a historical context, LSTMs were like 1990s stuff. So neural networks are still not popular, but like people came up with this idea, and it should make you wonder how exactly they came up with this, and it's really incredible that they did, because you have to really believe in an idea to push it this far when a certain topic is not popular at all in the literature or in practice. So LSTMs were 1990s, and then about 10, 15 years later, someone said, well, this whole memory element idea is cool, but it's taking up so much computation that we need to do something slightly simpler. So what they did was they took the same idea of uh, forgetting and remembering things, and they decided, okay, look, we're going to say like the motivation is more or less the same, that not all observations are equally relevant. Some observations you really want to remember because they're more memorable than other observations which might not be as different. So we need a mechanism to pay attention to some parts of it, and we need a mechanism to forget the rest of it. So in a sense, they're both converses of each other, right? And that's how this idea of the GRU was born, the gated recurrent unit. And note that this was about 15 years or 10, 15 years after the LSTM. So imagine you're doing research today and you start and read a paper 15 years ago, and that's how you get your idea, and like you build on that and improve that. Just an example of how the research process works. So anyway, the gating again starts similar to how we had the other gates. Takes a combination of input, hidden state by input times weight matrix, hidden state times weight matrix, and biases. And now what do we do? So, oh, sorry. Cool. So now once we have this reset and update gate, what we want to do is we want to use this, let's generate a candidate hidden state again. Note that this is the hidden state and this is the input. So there is no memory element. So we take, yeah, so far so good. For the hidden state, we take the input, we take the reset gate times the hidden state. So again, remember, if we reset goes to 0, then this entire term gets ignored. So your candidate hidden state does not rely on your previous hidden state. Yeah, this one gets cancelled out. So far, so good. Um, the next step we want to take, the next step you want to do is you also want to incorporate for an probabilistic kind of update. So in a sense, what you're doing is there is a candidate hidden state. So your Z, your update gate is a value between 0 and 1. And what you're saying is, I want to take some fraction of the previous hidden state, and I want to take the remaining fraction of the candidate hidden state, which may or may not depend on the previous hidden state, right? So with, you can imagine this is like saying, I want to learn something important right now versus associate some remaining importance with what I have learned before. And that is exactly what this is. There is nothing more to it. Again, like if you look at this entire thing at once, it will look complicated, and at least it looked super complicated to me when I started learning it. But then if you look at each individual element and what they're doing, it's fairly straightforward, and it starts making sense that, okay, now people experimented with this, it worked, it didn't work, and they published papers about it. But anyway, not spending too much time on that. Again, questions, stop me, pause. I will pause and I will explain things to you again. But so far so good. So you reset a certain element, you update a certain element with a certain probability that you learn, and that gives you this gated recurrent unit. The big upshot of GRUs and why they became popular was they were only marginally worse than LSTMs. So they did marginally worse on some large applications, and on small data sets they did better in a lot of cases. But this removal of this memory element caused a huge computation upshot, a huge bonus in computation. So it was much faster. So GRUs therefore became popular. Cool, good with that. Let's move on to, once people started realizing, well, RNNs work and we have these nice GRUs and LSTMs, they were like, well, the next thing to do is go deeper, go bigger, try to look for more applications where we can apply this and scale. So generally, the idea of using RNNs is when you want to translate one element to a certain output, when you translate one element to multiple outputs, or multiple elements to a single output, multiple elements to multiple outputs, and yeah, in different ways. So this is like sequence to sequence. This is probably also sequence to sequence. But yeah, different kinds of ideas for using RNNs. And the nice thing is they give us applications. So for example, if you want to generate a certain poetry given a prompt, so just as there is, LSTMs are better at counting sequence lengths over GRUs. There is a trade-off between the speed and performance depending on the use of LSTMs and GRUs. This is correct. Thank you. So poetry generation, it's like given a prompt, generate a whole sequence of items. Sentiment analysis is given a sentence, output a binary sentiment over it. Document classification, again, tell me the class that a document belongs to. Question answering is like, I give you a question, you select a subset of the text as the answer, or generate a subset of text as answer. Machine translation, again, similar, given a certain input document, after seeing the entire input, given a certain input sentence, after seeing the entire input, start generating the output. So English to French translation, for example. Named entity recognition is as you start seeing the input, start telling me what element or what part of the sentence it corresponds to. So that, again, a subtle difference between these two, but that's what you should remember. Fairly straightforward. So this was the whole recurrent neural networks idea. I mean, you already know this. So the question is, how can we make this more nonlinear? So what should we change to make this deeper? Is the question. Any takers? Any answers?
Stack more of the hidden states.
Stack more of the hidden states. Now, any more answers? I mean, I guess it's the same idea that you were going for. I was just wondering if we came about with research by asking you questions where answer wasn't clear. More activation functions for the components of the hidden states. More activation functions for the component. Yeah, in a sense, it's like, yeah, the stacking hidden states. So phi of psi of theta of whatever. It's like uh, maybe a diagram will better explain it. Yeah. So these things, instead of just taking non-linearities, how about we replace them with MLPs? So again, phi of psi, theta of psi of something. Again, this is just like representative of layers, right? And people thought about this. So they were like, well, just make it more expressive by replacing these hidden layers with sequences of hidden layers. And so someone created this whole set of experiments where they learned cells with 40 40 units in place of this single functional mapping. So again, a neural network is just a function that maps some real multi-dimensional element to some real class dimensional element. So essentially it's a functional mapping. So any functional mapping can be replaced by a neural network. That's what people mean when they say replace this with a multi-layer perceptron. And then you can place constraints on that where you want to say this belongs to a certain 0, 1 um, binary output, or you want to say real valued output or whatever else. But anyway, the point being, neural networks are also functional mappings. And that's why when you say like replace this with an MLP, that's literally what you mean. Like just instead of define function, take some arguments, the same function takes some arguments, applies an MLP and produces the output. Cool. So they did this, but turns out this was very expensive, but didn't really give you much. And they is and so the idea was like, yes, you need to replace them with MLPs, but you need to do something like that makes um, um, like non-linearity in the units versus layers of like stacked hidden layers are two different ideas. So currently what we're talking about is non-linearities in the units. But when that didn't work, people realized, okay, maybe we should just stack these hidden layers. But yeah, the initial idea was replace all these functions with more expressive classes of functions. And this is another way of doing that. So we go deeper in the sense we stack hidden layers. So now instead of just going to the next hidden layer, you also go deeper before producing the output at each hidden layer. So mathematically, what we're trying to do is we go from one hidden layer to another hidden layer, but now we can also like expand the size of this hidden layer given the size of this hidden layer, because there is nothing restricting us from doing that. So why not try and do that? So therefore this f is different from this f1 and yeah, and this fj. So those, each of them could be separate functions. And again, the key idea is you are increasing expressivity. And we will see a couple of examples of deeper recurrent neural networks. But before that, I want to drive home this one key idea of bidirectional recurrent neural network. So far we've talked about sequences where we get an input sequence and we produce an output sequence, or just unidirectional sequences, is what we focused on so far. But now it's a nice example Alex Smola offers here, where he says, for a fill in the blanks question, you can fill in anything in this blank, um, and it probably won't be wrong. You can also fill in more or less things in this blank, like I am very hungry, I am not very hungry. But when you get to the third sentence, where you have some context that comes after the sentence, here it would be weird to fill in I am very hungry, I could eat half, sorry, here it would be weird to fill in I am not very hungry, because you know that what comes after is I could eat half a pig, which implies that you're very hungry. So this is getting at the idea that the future matters to make a prediction right now. And if you only go in one direction, you're never going to get to come back and update that prediction. So, sorry, there's a chat message. Oh, my bad. Yeah, hopefully that was clear enough. So the future matters for making a prediction. And so it's weird if you fill in the same, if you fill in the word very, sorry, if it's weird if you fill in the word not out here, because very is clearly the right answer. Um, and so RNNs need to look at the future, and the simple, does this not, oh, this is a great question. Does this not violate the law of causality? Well, okay, so one way to think about this, and this is like a very hard I don't know. So one way to look at the causal flow is to say x1 determines x2, determines x3, determines x4. In which case you're saying I determines am, determines very, determines hungry. And again, this is a very hand wavy argument. Actually, it's not even an argument. This is not probably mathematically accurate, because these words are not causal. So I was going for a proof by contradiction. My point is these words don't actually determine each other. Um, there is actually some person who determines, like, or something that someone is trying to convey that determines all these words. Like there is a confounding factor. Like my hunger is determining me saying these words, that sort of thing. So the direction in this case doesn't really matter, because this is the real, yeah, the abstraction of language. So I was going for the word intention. There is a confounding factor of intention that determines the words you say. Um, and sure, there are the rules of language that create these arrows, but because of this confounding factors, it's not really a violation of the law of causality. But you're right that in applications where you are not allowed to glance at the future and you glance at the future, that is not practical. And this is a great point, because we'll have a slide in a couple of a couple of slides in, we'll see why this is a problem. So yeah, so the key idea being, we want to look at the future to make a prediction, in cases where we have access to the future, and I'll get back to why that's important. So flashing back to our old friend graphical models and conditioning and the Markov assumption, where we said one unit is dependent on its preceding unit, but not on the ones that come before it. So this conditional independence assumption was the Markov assumption. That condition on this unit, xt condition on xt minus 1, I shouldn't say x, I should say h, because x is the input. ht condition on ht minus 1 is independent of all h1 to t minus 2. Cool. That again, it's important to remember how to express these things mathematically. So there is a certain way to solve these kinds of problems, which is called dynamic programming. I won't get into the details of this right now, but I will give you an intuition, because this sort of, I'll at least explain the problem to you. So the problem is there is this joint probability distribution over the inputs and the hidden states. And the way RNNs are expressed uh, makes it such that current input contributes. Yeah, X. I believe this was H. X1, X2, H1, H0, H1, H2, whatever. So this Markov assumption says that this H depends on two. I should change color. Forget Markov assumption, just probabilities say that this H depends on the parents, which are uh, the X and the HT minus one, right? So every H depends on HT minus one. And do I want to start like this? Yeah, so I should rename. They probably started the naming scheme like this. Double check. Yeah, they probably started the sequence like this. Ignored the rest. Why you say that X is the I feel like this will. Okay, let's save time here, and I'll just cover this during the office hours in detail. But for now, what I want to say is, I don't want to say anything about dynamic programming. The whole cliques and factors and marginalization might be a bit too much for people to digest. Um, what you're doing is basically creating factors uh, where there are certain dependencies of this graphical, the way you can factorize a joint probability distribution based on the conditional independencies. So if you're saying that there is P of A, B, and C, but C doesn't really depend on A, so I can create a factor of P1, A, B, and P2 of C. And that's how I can factorize this into factorize this joint into two distributions where P1 and P2 might imply certain dependencies, like P1 might be uh, P1 might be P of B given A times P of A, and P2 might be P of C, just generally as an example. This is not what I'm saying is going on here, but the way you factorize this and then you solve each of these independently in order to combine them and then get P of A, B, C together. That is what this this HMM, like that is what this recurrent neural network is being modeled as, and that is how we are factorizing this whole joint probability distribution and using dynamic programming to solve it. So if you remember correctly, dynamic programming was like breaking up this problem into smaller chunks, breaking up that into further smaller chunks, and then solving these problems recursively to yeah, solving these problems to get back to your original problem. So that is the idea, except in the probability space, and I'm not explaining that because like it's hard to get into marginalization where most people might not know what that means. Although I would hope you do. But anyway, I have the office hours, so you can get in on Tuesday and we can talk about this at length. Anyway, we have spent a lot of time on this. Um, yeah. So the general idea, again, going back to bidirectional RNNs, is can we do this whole dynamic programming thing and like forward and backward modeling with backward sequence modeling with RNNs? And this might be much easier for you to digest, because this now just says take a sequence of hidden states going backward, take a sequence of hidden states going forward, and this sequential computation can then be combined in this direction. So just stack these two and use them for generating your output. This is much more straightforward than the whole probability stuff, but you realize now that in order to get here, you need to understand why mathematically this model will work. The problem with this is when you actually try it out, it gives you these kinds of things where it's not clear like that this is the correct prediction, but like it gets stuck and it keeps predicting these things. And can someone sort of at least try to guess why this happens? So I've trained a bidirectional RNN on predicting the next word in a sentence, and I'm getting this sort of output. This is my question. Student comes up to me and asks me why. What do I tell the student? Gradients, maybe. Well, not really. So if you look at the perplexity score, this is like a really good perplexity score. It trains really fast. So I don't think there are any exploding or vanishing gradient issues. It's fairly straightforward. Think about what you trained it on and think about what your test data might look like.
Is it trying to predict the most common letters if you're training it to predict the last letter?
Mm-hmm. That is a good comment, but not like that is what seemed, well, not again, that is also not what is seems to be happening, because it's not predicting the most common letters. The answer I was probably going for was, in your test time, do you know what comes after? Like, does the model see the entire sentence? You're running a prediction task, right? So you give it word 1 and 2 and you expect it to predict word 3. But during training, you gave it the whole sentence and you said, look at this in both directions and learn. So during test time, you cannot see the future. There are sentences for which you will not know the future and you want to make a prediction about the future. So clearly, like, the bidirectional approach relies on knowledge of the future where you do not have any. And therefore, your prediction task messes up because during training time, you've had this entire sequence, but like during test time, you don't. So this is irrelevant. That's the reason this sort of uh, approach can be used in, like, when you have sequence to sequence problems. So going back to what we saw very long ago, like, you need to know which kinds of models to use for which kinds of problems. And if you're making some assumptions on your training data, then that should hold for your test data. But generally, bidirectional RNNs do work well for sequence to sequence translation problems, and they worked really well for a very long time until transformers came about. Cool. So before we get into those the details of more complicated models, I want to take a minute to pause and like think about what we have studied before, and like in this field, like how progress works is often, so CNNs came about, and like there were residual connections in CNNs, and ResNets worked really well. So people naturally thought, well, residual connections work and RNNs. We have the same idea, right? We went deeper, which was the same thing that people did for computer vision, and they said, okay, go deeper, ResNets, VGG, AlexNet, LeNet, AlexNet, VGG, Inception, ResNet. And so when RNNs came about, they were like, okay, RNNs, deeper RNNs. Now we want to solve that problem where we said, are more, does adding more layers strictly improve accuracy? And we remembered that, yeah, well, you need this sort of sideline going inside so that you can learn, if even if you learn to ignore this layer, you still have like a shallower network that you can recover from a denser network. That was the key idea for ResNets. And the same applies to RNNs also, where people said, well, sure, you're going deeper, but like, shouldn't you like explicitly allow for this connection so that you can ignore certain hidden layers and like learn a slightly less complex network that performs better on the data? So yeah, people did that. They did exactly that. And residual connections are possible for RNNs also. Um, and then there are different bells and whistles on top. Like, okay, sure, you can still do the dense net and densely connected hidden layers, and you have to obviously reduce dimensionality at some point. If you're just concatenating, it's going to blow up. And there were other, so again, I'm not going to pause here, but if you have a question, then you can ask me to pause or post it in the chat. Um, is perplexity really a good metric to use for these tasks? That's a great question. I don't have an answer. I know people use it a lot, but I don't have an answer because I don't know the landscape of metrics to use for NLP tasks. I think, yeah, I don't know what to say to that. Like, I know the generic metrics, your blue, your accuracy, your F1 score, your precision, recall, all of those things. But that's yeah, no,
So
not sure.
I think it again depends on the tasks like we have at hand. So like if we see normal language modeling tasks like where we generate sequences, in that case, like perplexity helps us basically find out this probability distribution, and ultimately we are trying to minimize cross entropy in a way because perplexity is just exponentiation of the cross entropy loss that we have, like 2 raised to negative
Mhm.
of n. So lower like cross entropy, so low like basically low perplexity is better in a way like that from that perspective. But if we see for task specific things like that we have at hand later on, then yeah, perplexity is not that good. But it's not indicative of what actually correlates with human evaluation. So all of these automatic metrics that we have had for natural language processing, the drawback is like if we see the correlation with human evaluation, they are like completely different. Like it's completely 180-degree difference, like in terms of like how human agrees upon the solution and how these metrics are. It could help you basically determine based on, let's say, the blue and all different metrics, okay, how syntactically good like fluent your model is producing the output text. But the drawback is there is not like a good metrics based on testing the semantics of like, okay, how these models are producing text. So that is again like a really like still unsolvable question in natural language understanding. Like, okay, how do we understand okay what a like model is producing semantically, whether it makes sense or not. So yeah.
That's really helpful insight. Thank you. So yeah, I don't have a better summary than Jay just offered. Um, we can move on to overfitting and like, so okay, so right now in history, we are at a stage where RNNs are working well, um, at least better than most other techniques that are out there for language understanding. And now at this point, people are applying fancy techniques to RNNs, and like, they're going for, okay, we need to improve RNNs, we need to come up with tips and tricks to control training and like stabilize and like improve performance and all of those things. So regularization is more about like limiting overfitting. And it was, you have to imagine the situation is like, it is notoriously difficult to train great RNNs. There are a lot of things you have to do in, even compared to like CNNs. It's just really hard. So That's part of the reason why like people were eager to move on from RNNs, or at least somewhat eager, were because like at least I know a few friends who were working on RNNs at the time. It was just bad. Like it was very nice when it worked, very nice when it worked, but like getting it to work was painful. It's like the modern day GAN tweaking scenario. Like GANs are very hard to like debug for many applications, but when they work, they're beautiful. So this is just an opinion. So regularization in RNNs, they overfit. Now the problem is like there is a sequential dependence. So you also don't know at what point there was a problem. And again, that makes things worse because for neural networks, you can apply things like dropout without thinking much about like what you're doing, because these points are like independently being processed. But in RNNs, the points are sequentially being processed. So you really have to think about like in a time series, you can't drop the middle observation and say, oh, this is the same time series. This will on average be the same. Like randomly dropping out observations is not a great idea. So we might, yeah, the slide says we might miss relevant aspects in the coordinates. So say, yeah. So when people thought about like applying dropout, remember that we said phi could be replaced by an MLP. Like in those non-linearity cases, you can maybe just apply the dropout to the MLP instead of applying it to the sequence. And it kind of like that's one way of doing things. And this is just directly using how dropout was applied to MLPs into RNN universe. But we saw that, well, stacking hidden layers is better than just using these non-linearities. So in that case, how do we apply dropout? And there people came up with this idea that, well, you don't have to randomly apply dropout. These colors indicate like just random choices of dropout. Maybe you can have a certain mask and you can apply this mask for the same, like across the entire batch. So the same mask is applied across the batch. So in a sense, you are maintaining some notion of randomness, but also some notion of structure. So if you lose out on some important aspect, you lose out on all the same important aspect for all those subsequences. And then the next time that batch comes in, maybe you apply a different mask to all of those, but like semi-structured dropout, I guess. So that was this idea of variational dropout. So the masking process, so typically what you might do with dropout is just randomly select neurons to drop out. But in this case, you apply a fixed mask for the across the entire batch. So if you're losing out on something, you lose out on all of the same element across all of these sequences. And so you maintain some notion of structure. So I mean, I don't know what more to say. Does that help?
So like basically just remove the whole sequence of layers in between.
No,
Is it like that?
remove specific elements only, but like in a structured way, not randomly. So
Yeah,
the
in a
same mask
sequential way.
is applied for the batch.
Oh. Okay. Yes. Okay. Somewhat understood.
Cool. Yeah, I'm sorry. Honestly I haven't read the paper, so I'm just verbatim repeating what is being explained.
So, Swapnil, in this case, is it
Yeah.
like we decide okay when to apply dropout and when not to apply? So like, or we every time we apply some amount of dropout.
During training, so the yeah. Oh, sorry.
No, yeah, that's it. Yeah.
Um, Again, I haven't read the paper, so this is what I understood from the video. But actually, hold on. The easy thing to do here is to show you guys how to read papers quickly and get a key idea out of it. And I believe I'm sharing the wrong screen. Oops, sorry. Oh, I'm sharing the wrong screen. Okay. Variational dropout. We want Gal and Karamani. Where is? Okay. I don't know if this. I'm guessing this is. I guess this is the idea. Cool. So recurrent neural networks stand at the forefront. Major difficulty is the tendency to overfit, with dropout shown to fail when applied to recurrent layers. Recent results offer a Bayesian interpretation of a common deep learning technique such as dropout. The grounding of dropout in approximate Bayesian inference suggests extension of the theoretical results, offering insight. We apply this new variational inference-based dropout technique, assessing it in language model. The new approach outperforms and to our best, to the best of our knowledge, this extends our arsenal of variational tool and deep learning. Okay, I didn't get much from this, to be honest, but the general idea is they try to explain a new method of dropout using the theory of Bayesian inference, right? Now, the question I want to get to is like, what are they really doing? And this is probably going to be, oh, this figure seems nice. Each square represents an RNN unit with the input and output to each RNN unit. Colored connections represent dropped out inputs with different colors corresponding to different dropout masks. So a dropout mask is telling you a dropout mask is a vector of zeros and ones, right? So it's saying instead of at every time step changing the dropout, you're saying at every time step apply the same dropout mask. The proposed technique uses the same dropout mask at each time step, including the recurrent layers. So I guess that's like from an application perspective, that's about it. Like instead of random sequences of zeros and ones at every hidden layer, you're saying that at the first hidden layer, I will use the same dropout mask. At the second series of hidden. So these are all like like deep recurrent neural networks, right? So these are multiple hidden units. At each stage in the layers, use the same dropout masks. The blues, the greens, and the reds may still be selected randomly, but the point is they are uniform across all hidden units in that layer. Is this better, like more clear to people now? Yep. So yeah, you just maintain some notion of structure, and then they have a bunch of theory explaining why this works. But the idea seems fairly simple. Yeah, this is. I was hoping for maybe another diagram, but that's a bit much to expect. But it's fine. So that was the idea. Let's get back to the slide. So hopefully, I also explained how to go to a research paper, take away exactly what you want, and not spend more time on it than necessary. The time aspect is important because you will be spending a lot of time reading research papers. And this, I didn't know I would do this. I don't know if I have done this correctly, but yeah, I just wanted to walk you through how this works for me. Okay, let's go back to slides. Move this out of the way. Place slides. Cool. So variational dropout. Yeah. Other ideas include skipping observations in the sequence. So you want your network to be robust against like skipping a hidden state update. Again, like all of these ideas are motivated by, most of these ideas are motivated by something that worked in practice, and they tied it back to some simple intuition, and they were like, here you go. But it's not necessary that things work based on the intuition. So sometimes, a lot of times, the intuition is based on comes after things working. So yeah, this is fairly straightforward. Sometimes you keep the hidden state the same. There is parameter averaging. I'm not going to spend time on this. There is stochastic weight averaging. Again, not going to spend time on this. If you want the details, read the papers. I am pretty sure. So swag and stochastic weight averaging, the follow-up paper, I think, is now in PyTorch. So it was really that helpful that it's now a feature in the library by default. And you're probably doing it if you're using PyTorch today. I think so. But yeah, this paper in particular, he says, this first paper in particular, he says, has a lot of tips and tricks about how to make RNNs work. So definitely sit and read that paper if you want to get a better idea of. So these tips and tricks will also translate to, like, in the future when we have more sequence-based models. That gives you an intuition of what tip might work, what tip might translate over, just as like residual connections translated from CNNs to RNNs, so on and so forth. So it's always useful to understand tips and tricks. Let's move on to, how are we doing on time? Okay, I think we're good on time. Let's move on to attention, which is a super important part of modern language models. Attention, multi-head attention, self-attention. The key idea is that there are different relationships in translating sequences. So my name in French might relate very closely to my name in English, which is part of a whole sentence I'm translating from English to French. But when I am translating, I want my network to pay attention to what my name was in English because it's very close to the name in French. Similarly, for other parts of the sentence, so hello might be very important to bonjour, world might be very important to le monde, and yeah, so on and so forth. The period might be very important to the period. But anyway, the general idea is somehow we want to learn this set of weights that tells us which part of the sentence was most important to attend to for the output. So the way the way the people, I think there were two papers simultaneously on attention based models, Patana and someone else. But the way the people framed this problem was like an attention layer explicitly selects some related information. So it's like saying, given a set of like a knowledge base, like there is some knowledge base, you add a query, you input a query to it saying, this is my word, what is the most important word for this word that I'm trying to output, and it gives you a certain key, or you add a query, it gives you a certain output which says this is the word you care about. And the way it does this is structured more or less like a database. So it's like a key value pair, which contribute to this attention layer. And then when a new query comes in, you match these key value pairs. You match the value pairs basically to the query and then return a certain output. Yeah, I think that's all I want to say. So before diving into the math. So some query is some query dimensional vector. The memory consists of key value pairs, with keys being key dimensional, with values being some value dimensional. This is like a very general way of saying things. So I'm not fixing any dimensions. They might be different for each of key, value, and query. Now, when a query comes in, you want to calculate n scores with how much the query matches which key. Going back to this diagram, you want the query to match one of these keys, and you return the corresponding value to it. The typical way people used to do this was like you just take the max of the output. But now the problem with taking a max is that you cannot take the gradient of the max because it breaks this flow. Like it is not a continuous function. And so people said, well, instead of max, let's just use a soft max. Now you have a continuous function and you can take the gradient over this function. So that's how this output emerged, which is like a weighted sum of values for a certain query. The alpha that I didn't speak about much is like a function that is a score function for how closely this query matches this key. And so one of the ways of doing, the simple way of doing attention is just take dot products. So your alpha is simply like a dot product, and you normalize it because the query and key dimensions might be really great. In this case, you just take them RD. Again, this is an example. They might be different dimensional, but you just have to normalize by the dimensions in order to avoid it, the scores blowing up. And the same in matrix form gives you the vectorized version. So this was simple, like this was dot product attention, but like what if I want my attention scores to be more than just this? Well, just add, like parameterize it with a neural network. Like we said before, like the reason a score function is a mapping. It takes two arguments. Alpha takes in Q and K. Ooh, I should be writing this. Alpha takes in Q and K and maps it to some output, right? The same thing, except now we do it with an MLP. So alpha takes in some Q and K and it produces some output. Except now it does this by applying a certain weight matrix and passing it through a nonlinearity. So we can simply parameterize this with a multi-layer perceptron, which is like a single layer, single layer multi-layer perceptron with an output size of 1 because we're mapping it to a real value, which is this could be our score function. And we'll get into more ways of parameterizing attention, but this is the key takeaway, that there is a certain database that you learn from the data. You match, you learn these parameters for calculating this score function that tells you what is the closest match in the training data for this query that comes in. I will pause if there are questions. Okay. Seeing none, the way you apply this now, so far we've spoken about one query, right? And we have a whole sequence of words coming in. So how do you learn attention over this entire sequence? Well, simple, pass all of them into the attention layer. So in practice, like the way you would want to do this is that you learn your key value pairs by passing in your data to this attention layer. And then once you start having queries, it produces certain outputs, and then you start decoding your sequences, whatever, right? Like practically, the way this works is like, what are queries? That is a great question. Can someone answer this?
So queries are nothing but like, let's say, whatever representation you obtain during the decoding stage. Sorry. Yeah, queries are, sorry. So queries and the values are the same thing. So they are basically the, if you think of this as attention, so there are three things: keys, queries, and values. So keys and values are like the encoder hidden states that we have. Query is basically the thing that you will be decoding and generating some representation and comparing it with the encoder hidden states. So you are basically whatever the decoder hidden state, let's say you have, you compare that with the encoder hidden state. So you are querying that with the values and the keys that are there and finding out, okay, what is the highest match or based on the score, like what things are relevant from this encoder hidden state, and using that further on in your like decoding stage. So queries are for the decoding side, the decoder hidden state that are there before the applying attention. Is that clear? Okay.
Yeah, cool. Thank you. So, okay, so far we know what attention is now. We know like this is some sort of querying mechanism where you have an encoder, you use it to learn some importances. And when you're starting to decode things, you have a certain query and you get back certain outputs that are a result of what this attention tells you need to learn from the input data for this generating this particular output. What you want to do with attention now is to incorporate that into recurrent models, which is the current slide that we're on. So in a recurrent model, you have your encoded inputs, you have them passed into the attention layer. And while decoding, you rely on this attention layer to tell you what parts of the output depend on what parts of the input. Now, this small block can actually be improved and used in different ways. And that, yeah, I think that was the key idea for transformers was like, well, we're doing things sequentially. How about we parallelize things? Like there were a lot of possibilities to once attention came about. People started like looking into like, okay, how do we expand this concept such that we break this need to do everything sequentially for recurrent neural networks? Because that was the big problem. Like in RNNs, there is sequential computation, and that is not easily parallelizable. You can throw as many machines at it, but until you break this dependence, and like you can't easily parallelize the computation. So with transformers, the real cool thing that came about was now you can actually parallelize things. And the way you parallelize things is by using this idea of self-attention. So in self-attention, to start with, just think about it as everything is done, all of these encodings are passed into the attention layer, and we don't have any sequences right now. So you are forgetting all of these words, the order of all of these words. So if I add, I am very hungry, and if I input, I hungry very am, it's still going to produce the same set of outputs as I am very hungry, right? Because we are currently not caring about this directional arrow. And I'll get back to like clearly we are missing something, right? Because this directional arrow matters. Because you want to, if in a sentence translation task, like order matters, for example, like you want to translate something into meaningful words in another language, meaningful sentences in another language, not just meaningful words, but in a random order. So position matters, but right now, ignore position. Just think about how you want to encode this. And the way you encode this is by using this mechanism of self-attention, where everything is passed into the attention layer, and you get your output based on whatever these queries are. The architecture for transformer then adds this positional encoding before what it calls multi-head attention, and we'll get into all of these layers individually in detail. But the notion is like, okay, we add some positional encoding separately, but then we use like parallelized attention, so that now we break this dependence on like doing things sequentially, and now we can really scale, because now we scale with compute, unlike previously in RNNs where you had to do things one after the other. So what is positional encoding? What is multi-head attention, and what is this position-wise FFN and stuff? Let's dive into that. So this is one transformer block for the encoder and the decoder. There is, yeah, multi-head attention. So what multi-head attention is saying that yeah, cool. So your multi-head attention, the simple thing to say is like it consists of multiple independent attention blocks. Yeah, I mean, I don't know if Jay wants to add something to that. I feel like might be better at explaining this than I am.
So like the idea of multiple attention blocks is, let's say you are having this single attention block. So the idea is having this multiple attention block adds more expressive power. So let's say one attention block maybe captures some representation, then the other might capture some different representation. One is focusing more on syntactic way, other is focusing more on semantics, like that way. So the main goal was to have like multiple such blocks, which each of this capture like separate information, and like all of the information is further then clubbed and passed on to like the other layers forward. So like it is just done to increase the expressive power of the network. Yeah, but the idea is the same. Like you add this multiple things to learn different structures, like so where each attention had learned something different representation.
That is useful. That is very useful. So yeah, you hope that by increasing expressivity, you allow your model to learn different aspects or different relationships within a sentence, like you said, whether that's syntactic, whether that's semantic. I think that's all there is to say about that topic. And Deep shared a very useful link. Distill.pub is a very cool blog post journal esque website that has a very nice JavaScript driven interface that does all of these visualizations for you in browser. Definitely check that out. Distill.pub. Anyway, back to attention and multi-head attention. I think we've seen what multi-head attention is, so we can go on to position-wise feed-forward networks. The key idea of position-wise feed-forward networks is to, once you have this multi-head attention and you have passed it through whatever your layer norms are, you want to reshape back into a three-dimensional output because you have averaged over the last, well, you haven't gotten to layer norm yet, but you've averaged over some layers and you've created a lower dimensional representation and you want to turn that back into the original dimensionality that you need to pass on to the next section. I don't think I want to say anything more about that. What I want to talk about though is layer norm. The idea behind layer norm is similar to batch norm, except that in text versus in images. In images, you had batch norm because you had this dimensionality or height and width, and you wanted to average in a sense over an image instead of across images. But now in text, you want to use the feature dimension to average over, and that is the key difference between layer norm and batch norm. This is literally like the code for taking the mean of the batch versus taking the mean of the layer. I guess yeah, that's all I want to say about that. Positional encoding, this is useful. So we said before that we break apart, like we break this dependence of an RNN to train everything in a sequence by using this multi-head attention idea. But we also do need to consider sequences because there is an important relationship there, and the word order matters for a sentence to make sense. And so we incorporate this idea of a positional encoding. So for each word, you calculate a certain function, a certain value determined by a periodic function that in a sense indicates the time value of that word. So if it's at position 2 or position 3 in any sentence, it will have the same relative value depending on these parameters that you learn. Again, like the idea is just like you want to capture the relative relationships of position, but you don't want that to be the limiting factor in computation. So, well, just calculate position separately and then treat everything as the same and add this positional embedding to it. And that's how it works. Again, like this is intuitively it makes sense, but you don't know until you train it whether this actually works or not, and it turns out it did. So yeah, finally, when you are predicting, after you have given it all of your, the way prediction works is that you have all of these inputs of previous times as keys and values. And then when you add a query of the input at time t and the key and value, you use self-attention to arrive at a certain output. I feel like we've been over this workflow, but hopefully this slide makes it much clearer. And transformers worked really, really well. So again, like to go back to the whole architecture, we've seen like the we've seen the positional encoding, the idea of separating position and embedding. We've seen the multi-head attention idea that really allows us to parallelize and focus on relationships between the output sentence and the input sentences. We've seen why normalizing across layers is necessary for words as opposed to batch norm for images. We've seen position-wise feed-forward network, which is essentially just like outputting a certain representation, a certain dimensionality. And we've seen overall that this transformer block is basically what is repeated in transformer-based architectures in order to learn a certain, in order to build the networks. So let's now take a look at like what is going on, like what kinds of like this, just a popular transformer-based model, and why transformers got popular. So BERT is,
yeah, just one more thing to add. So the idea for having like this positional, the feed-forward network about the multi-head attention was to add more non-linearity. Right? So generally, it's a neural network because like if you see the dimension are the same, like if you pass it's just in positional encoding, it's extending the dimension, then again shrinking like the dimension. So the idea is having this more non-linearity such that it learns more better representations. And again, yeah, it is also using this residual connection. So that is also one thing, yeah, I would like. And yeah, it is like basically just MLPs, like if you see on a higher level, all of these are feed-forward networks that are like designed in such a way that we are able to process this and also have this positional encoding informations too and parallelize computations. I think, yeah, that's all.
fair enough. Cool. So, getting back to BERT, BERT is one of a class of transformer-based models that worked really well. The motivation for this was that like there is a lot of transfer learning taking place in natural language processing, where you use pre-trained models to extract words and sentence features or embeddings for the new task. And you don't actually end up updating the pre-trained models. But the problem with this is like in some cases, like these embedding based models don't capture what you really need for the task. So word2vec ignores sequential information because you have words, I am very, and this gives you representations for I am and very, but like it doesn't account for this sequence or position idea. So that's why word2vec like ignores this information, and so it's hard to use just word2vec without updating it as a pre-trained model. Language models typically look in a single direction, unless you have bidirectional RNNs, but then they don't do as well as larger language models. So like you have a trade-off. But anyway, there are problems with pre-trained models. Such that they could not be used. Like there was not a general pre-trained model available for a bunch of different NLP tasks. Like we had ResNets available for a bunch of image related tasks. So even today, ResNets are ULM fit was the first model before transformers, which paved the way for transfer learning. So there's a link to ULM fit. I think it's by fast.ai, right?
Yeah, it's my fast today. I think it was like in similar time period, like around 2017, but yeah, or like late 2016. But yeah, it used AWD LSMs, which showed like using transfer learning for NLP is possible. And then this transformer models came, which literally changed the way we look at NLP.
That's very nice. Like, thank you for the historical breakdown. So So at this stage now, we're looking for like general purpose transfer learning models that perform really well but for a bunch of different tasks. So in the image domain, we had ResNets, which basically give you embeddings of images, and then you can do whatever the hell you want downstream with it. But this ResNet learns a good representation that is transferable to a bunch of different tasks. We want a similar thing for NLP, but the problem is we don't have it yet. So well, someone decided to use transformers to build this. This is the same thing. A fine-tuning based approach for NLP, where you have a general purpose model before, and then you fine-tune it only the last layer on a different task. So the goal is the pre-trained model must capture sufficient data from sufficient information from the data. And you typically only need to add a simple output layer for a new task. So with this motivation, the BERT architecture was created. So BERT base had 12 blocks and 78 hidden size of 768, whereas BERT large had 24 blocks with a size of hidden size of 1024. The purpose of telling you these numbers is just to give you an estimate of like, in a hand wavy sense, parameters versus compute. So if it has 110 million parameters, it's probably much cheaper to perform computation and train on than 340 million parameters. On the other hand, BERT large might perform really better than BERT base. But anyway, the general idea was it was trained on a large scale corpus with a lot of words. The architecture, actually I haven't prepared this for the class today, so let us wing it. Positional encodings or positional embeddings, or if Jay, if you want to, if you want to take
yeah, so for the BERT architecture, I think it follows a transformer architecture, and it was based on the idea of GPT models that were like before this. So generative pre-training transformers models. So which had this idea. So they tried like scaling up the transformer models, like adding more layers, and it tend to perform well on that particular, like the having more layers. So that was the general approach. So for the BERT also, it was the same idea, but the objective for the BERT was different. So like basically instead of generating the text and treating it as a self-supervised problem, so they chose it as more of like a closed task. So where they had like two things. So first is, let's say we have like two sentences, one after the other. So for that particular reason, we have this segment embeddings. So where the segment embeddings EA represents the sentence A or the sequence A, let's say, and EB represents the sequence B. And the BERT model has to predict whether, like given some sequence A, whether sequence B is like the consecutive or follow-up of the sequence A, or like is it not? So it's a classification problem, but the answer is yes or no. So that was the one task. The other was like the BERT is more of a mass language models. So the idea with mass language models is that so in the training time, we don't generate tokens one by one. So the idea is we mask few tokens that are there in the sequence, and based on that, like we tell the language model to predict, okay, what should be the token that at the mask place. And for like coming up with masking scheme, so like they decided, so basically let's say they decided for the total corpus that is there, like let's say for batch, and I think the batch sequence was 512 tokens at a time, like sequence length. So for that, like they were doing this 15% randomly masking tokens. And for this, out of that 15% also, then there were like some way, okay, so we should not always, the idea was, so for that 15%, then they decided okay, about some distribution. So like 80% of the tokens would be replaced with the mask. The other 10% they were randomly picking, like so replacing some tokens and like trying to have, okay, because every time in real world scenarios you won't have like text which would be proper, and 10% time they kept the same token. So that was their goal for like this particular training. And here transformers of bidirectionality is used. So in this case, the BERT based models are if you see bidirectional because you have access across all the context that is there, like across the mask token, because based on looking at forward and backward, you decide, okay, what would be the possible mask value. So that is a way for this particular word-based language models. So like this generating some representation, and then representation is forward to a feed-forward network. So in transformers, if you see most of the pre-training tasks, so we have this general, the base model that we have, let's say the BERT one, and for fine-tuning or like for transfer learning, we just add like a fully connected layer or a top head on the top, like depending on the task. So as if you see like this particular example, so where we pass the same sequence, we have this BERT model as the uh, base model we have, and we have like we change the head as per different task. So the idea of BERT is just to come up with some good representation, which can be further like used by this particular head, and we just fine tune the weights of the head in this case. And what
Cool.
should we add? Okay, yeah, and I think maybe like to just add more context. So, but like basically, as we said, there are two sentences: sentence A and sentence B. So sentence pair task. Like, so for that, like the SCP token is used as a separator between sequence A and sequence B. And one more point to add. So here we assume that there are two different sentence pairs, but ideally it is not like they would have like this two different sentences only. We just want to identify, okay, whether let's say the sequence B is followed by sequence A or not. So it can be at basically within a single sentence also we can have this two sequence. And as a language model, we also have certain other tokens as well, like POS token and different other, like, so in this case there is a start token, end token, pad token. I think, so yeah, probably.
Yeah,
That's it.
that's very helpful. Just to conclude, like the same things that the same general purpose pre-trained model can be used for a bunch of different tasks in the same way that he explained. So named entity recognition. This again goes back to the whole Karpathy's types of RNNs and types of tasks and those diagrams that we saw. So named entity recognition is a many to many prediction where you want to give it a set of sentences and get out the labeled entities. Question answering was a sequence to sequence task where you give it a question and it gives you an answer. So again, like the goal was accomplished with BERT, which basically gave you the output by fine-tuning a final layer on the same pre-trained on top of the same pre-trained model for a bunch of different kinds of inputs. And then BERT has been succeeded by different kinds of models. Again, transformer based. So we are still in the age of transformers, with GPT-2 also being a class of massive transformer based models. And I think that is the last insight I will give you, that transformers have been used for a bunch of different tasks, not just language, but also in vision. I feel like there's a lot of other application areas that I'm missing, but like just biology. I don't know if protein folding used transformer based architectures. I should look that up actually, but protein folding is this.
I think they are using transformers probably. It is a sequence.
Yeah, I'm just looking up AlphaFold transformers. GPT-2. Yep, AlphaFold uses transformers. So AlphaFold is there is this big problem that has to do with some kind of protein prediction, which has been like there has been hundreds of years of at least 100 years of research on this. I'm going to say 50. But big deal in the scientific community. Probably the biggest scientific breakthrough in the last decade. Protein folding. Look it up. It uses transformers. So generally, the sense is that, well, mean, protein folding might also be like a word sequence to sequence task. So that's my transformers might be working well, but so it might not be the best example of a different field. But yeah, thank you, Deep. So you can make music using transformers too. I feel like that might also be like a
Yeah, it's a
language
sequence.
oriented task.
I think main maybe user of like transformers like in a different field should be probably like surprising a sort of vision. So where they treat like the pixels in the image as a sequence, but and then you are like basically unfolding this pixel sequences and like trying to deal with that. So that is like really important because if you see images as like different say pixels from form a patch and that patch represents something, but transformers are able to pick that up and like deal it like let's say break it down into a sequence and then also like solve that problem. So yeah.
This is fair. Yeah, I was going for something even more unconventional, but yeah, fair enough. Yeah, why not vision? So anyway, I
So
think we can
would
end the
you
lecture there.
like to talk a bit about like the particular ethical concerns like with regards to use of this large language models that are there like nowadays? Probably.
This is thank you for this. This is yeah, and since we have time, this is super important to cover. Even if we did not have time, I should have made time for this. But thank you. I think so. The root cause of the problem, or at least the origin of the problem, is, and I feel like we've examined this in Vision for a bit. We actually did examine this in Vision, where these large models trained on data sets that have not been carefully curated learn some biases, and then no one really checks for these biases until they come out in weird applications, like certain races of people don't have their faces recognized, and certain races are more likely to be labeled as criminals, and those kinds of things happen in Vision. But you have to realize that even in language there is a certain bias, like certain religions are labeled as terrorists. So if you for instance, I think there was this example where large language models were given a prompt, and I'm not sure if this was GPT-3 or something else, but I mean, I would be willing to put my money on this being GPT-3. That you gave it a prompt, a Muslim man walked into a bar and something like that, and it ended with like a terrorism joke, and that's just really, really, really bad, because these models are being deployed at scale in production across multiple companies, and it is unfathomable how much downstream harm this will cause. And this is one kind of bias. There are hundreds of biases that it has learned. um, um, Resume. So if you use language models and resume filtering men versus women, it might actually just tell you that you shouldn't employ women, because there is an existing hiring bias and your data set is primarily men. um, Again, like
This
out
was
here.
true like yeah, this was true like it was like detected by Amazon also. Amazon's recruiting system and they were biased towards women based on
Yeah,
filtering.
and people are actively, like, they do act after they realize these biases exist. But the problem is, like, um, that should, like, someone should verify this before actually deploying it, right? And of course there are challenges with like verification, but especially if you're deploying it at scale, then you have the resources to actually verify that. So you please be careful when you're using these models. Like, if you have something trained on a Reddit data set, it is likely to have toxic comments. Reddit is widely known for not like being an unfiltered platform because of anonymity. But the same unfiltered platform can very quickly turn toxic. um, Microsoft released a chatbot to be trained by talking to users on Twitter, and guess how soon it became racist. Started spewing anti-Semitic slurs and stuff like that. It doesn't take the internet long to corrupt a model. So if you're training it purely on unfiltered internet data, be very careful about the kinds of applications you're applying it to, because there might be very easily massive problems unfolding under your um, um, super well, slipping under the radar, and you don't want to be on the receiving end of the blowback. Um, I don't think I want to say more about language
So,
models. Like,
so like one more example that I would like to share. It was very recently in news as well. So one company was trying to use GPT-3 model for medical as a chatbot for medical use in like, and they were trying like testing the more this chatbot, and like the problem was like the chatbot one patient was like having some like let's say was ill, and the chatbot told to die that pace like patient to die. So like you can answer like understand what are the consequences of having this models like chatbot GPT-3 based and all this large language based models sort of. And
okay,
again, and also the second thing that should be in a way highlighted is like currently if you see the research more of it's like you stack more layers, you obtain like let's say point increments in the metrics, you perform better, you are at the top of the table. But for like having that points of like improvement, like how much compute you are spending, because these models are now getting bigger and bigger. Like GPT-3 is 1.75 billion parameters. So you can understand like this. We is that point increment in the performance justified to like the computation we are spending on? Because this is like the one that is like shown to us on the paper. There are like several experiments that are being carried out like behind the scenes. So can understand like how much competition is also like spared for this.
yep. So yeah, that reminds me of a couple of points I should make. Um, before that, though, Deep shared a very good link about assessing gender bias in machine learning, a case study with Google Translate. There is also the stochastic parrots paper, I thought, that
Yeah,
had a lot of drama
that was
associated with it. You can just Google stochastic parrots and it should show up. Um, the point being, like, there is a business value associated with large language models. And if you're a big business, you definitely don't want more criticism of these models that are very valuable in production. So that is where the disconnect happens between like ethics and research, ethics and deployment. So again, I don't have a lot of comments more than what you can already find online, but I will point you in one direction particularly that ah, I forgot what I was going to say. Uh,
is
I
it
think
sparse models that you are maybe talking about?
no, not sparse models. I was going to say something. One of the things was looking at more efficient models.
So I
So
think that
data. Oh yeah, data leakage. Sorry. But
yeah, sorry, go on.
so when you train large language models on data sets, a lot of times, and this was a popular case with a Korean company, I think South Korean company, that had a chatbot that was trained on a bunch of private data of couples. I don't know if they obtained it with or without consent. I assume there was consent, but like it was trained on private data of chats between couples, and a lot of that, like it started outputting certain nicknames if you put in certain names. So you sort of realize that people call each other nicknames. It started outputting addresses when given certain prompts, and these were addresses of real people, just because it was not filtered out when you're training on that data. So there are these nuances. Like, the larger language models get, the harder it is to keep track of exactly what it is learning. um, Interpretability just goes away as you get deeper and deeper, unless you have the right framework to examine this in. And yeah, thanks for the pointing the paper on the dangers of stochastic parrots. So this actually happened with the Korean company, where they released this model, and then suddenly they had people querying the model to get addresses and nicknames of people, which is like personal information. So be careful that like you don't end up in such situations. Like, there are lots of challenges associated with large language models. Compute is just one of them. Data leakage is another one. Ethics and bias has a lot of sub problems to study with respect to language models. And then there is always like, what languages does this really work for? Does it actually Is it biased against marginalized languages and communities that use those languages? Yeah, again, lots of questions to be answered, lots of interesting research to be done. But hopefully, like, this gives you a set of warnings about, like, yes, large language models are awesome, but also have this section in your paper that critically examines whether this model is actually good or not. With that said, and on a very good note, we bring this lecture series in this summer course to an end. I will be around for questions for another 10 minutes, but I can pause recording here.